Good day, everyone. We are the group number 2, and today we will present our project estimates of a two-story residential building project. So, for this presentation, we will be discussing the project description, a brief explanation of estimates, sample computations, wheel of quantities, and frequently asked questions. So, for the project description, the project is located at Bloomfield Subdivision, Barangay Lumbia, Cagayan de Oro City. The residential structure has a total floor area of 208.57 square meters built on a 216 square meter lot. The design follows a modern architectural style using a reinforced concrete structural system. The structure is planned in compliance with the National Structural Code of the Philippines, or NSCP, to ensure safety, durability, and structural stability. The project also includes modern residential finishes, insulated roofing, and elevated floor levels. These features help improve the functionality of the house while increasing protection against flooding and environmental conditions. Overall, the project aims to provide a durable, safe, and comfortable residential structure suitable for modern family living. For our estimates, we first computed the structure excavation volume for the column and wall footings. This computation determines the amount of soil to be removed from the natural ground line in preparation for the foundation works. The estimate is based on the 14 primary column footings together with the connecting wall footings. Next, we estimated the formwork quantity for both vertical and horizontal structural members. The formworks include the plywood and coco-lumber bracing needed to shape and support the concrete while it cures. The calculations over the sides of columns, beams, and footings. We also computed the structural concrete volume for columns and footings using Class A concrete. These estimates are important because they help determine the required concrete materials for columns, beams, and footings up to the roof beams level, ensuring accurate batching and material ordering during construction. Another major part of our estimates is the reinforcing steel bar or RSB weight for the structural framework. This includes the total length, number of pieces, and weight of the formed steels before use for columns, beams, and footings. The computation also considers slab splices and standard hooks needed for proper structural reinforcement and compliance with the design standards. Lastly, we estimated the required quantities for masonry works and reinforcement. This covers the number of concrete, hollow blocks, plastering materials, filling materials, tire wires, and reinforcing bars required for the wall construction. The calculations include all masonry walls for both floors and the structure to ensure accurate material estimates and efficient construction planning. That concludes.
Hello, I am Carlos of Carbonilia, and next up is our sample computations. I will be presenting one sample calculation each from our computations of reinforcement steel and masonry works. Respectively, these are laboratory activities number 7 and number 8. So allow me to present here a calculation for laboratory report number 7, which is on the reinforcement steel quantity survey. For this sample computation, we have the reinforcement steel quantity survey of the tie beams of the structure. This computation was done and written by Renz Norel Belen of our group. So first, on top, we have here on the left side a drawing of the tie beam layout, as shown along with the footings and columns layout. In this drawing, we can see the different tie beams, and they are labeled based on their dimensions, such as their lengths. In this case, there are 13 tie beam dimensions, so they are labeled from TB1, TB2, up until TB13. On the right of this top image, we have drawings of the cross sections of the tie beams and the columns. If you look at the tie beams, we can see here the layout of the longitudinal bars and the stirrups, which was used as the basis for this calculation. But please note, this calculation covers only the reinforcing steel for tie beams, while the computation for the column tie beams, the column rebars, were done by other members. So moving on, to start the calculation, there are a total of 18 tie beams whose dimensions have 13 variations. So to calculate the reinforcing bars, we need to compute for the total length of these tie beams. So here, we first calculate the lengths of the tie beams from TB1 until TB13. For example, TB1, as you can see, one of them at the top of the drawing is slightly smaller than 5.55 meters, where that dimension line is on center with the columns that TB1 is connected to. To get the length of TB1, we simply subtract twice of half the short dimension of the column, so just 0.25 meters, from the displayed dimension line. And this gives us a length of 5.3 meters for TB1. Then the calculation proceeds to each of the different tie beams all the way up until TB13. With those calculations, we can then calculate for the overall length of the 18 tie beams, which is 40.52 meters as shown here. We then multiply this by 8, which is shown as the number of bars in the cross section, and we get a total of 324.16 meters. Then we calculate the extra reinforcing bars that are a third of the length and found at both ends. This results in 108.05 meters. So in total, the tie beams requires 432.21 meters of reinforcing steel bars. Then we can calculate for the weight of the beams. First, we get the unit weight, which is 16 squared over 162, which equals 1.58 kilograms per linear meter. Then we multiply this to the total length, which is 432.21, and we get that the total weight of the 16 millimeter rebars in the tie beams is 682.89 kilograms. So next, we are going to solve for the stirrups. So first, let's solve for the width and depth that is available to the stirrups, considering the fact that the concrete covering, as said in the previous slide, is 50 millimeters. We must also consider that in the previous slide, it was mentioned that the stirrup specifications is that they are made out of 10 millimeter diameter, spaced at 100 millimeters on center. So with that, the width available to these stirrups is 150 millimeters, with a depth of around 300 millimeters. And next up, we need to calculate for the number of stirrups that we need. So based on the total length of the tie beams, we have 40.52. Divide that by the spacing, which is around 100 millimeters, and we get 406 pieces of stirrups. Next, we calculate for the length needed for each stirrup, and we get 1.1 meters, that is for each stirrup. Then for the unit weight, we need it for the calculation of the total weight. That is 10 squared over 162, which leads to 0.617 kilograms per meter. So with that, we have a total weight for the 10 millimeter bars of around 275.56 kilograms. You add this together with the total weight from the 16 millimeter bars, and we get 958.45 kilograms of reinforcing steel. So, as a summary of all these calculations for the tie beam reinforcing bars, for the longitudinal bars, we need 73 pieces of 16 millimeter diameter by 6 meter rebars. And for the stirrups, we need 75 pieces of 10 millimeter diameter by 6 meter rebars. So, with laboratory activity number 7 out of the way, let's move on to number 8, which is on masonry works. So for this sample calculation, it was done by yours truly. Here we can see an image of the different walls for the house divided into A1, A2, A3, A4, and A5, involving both the first and second floors of the residential house. I was assigned in area A2. Here you can see a zoomed in. It involves the dining area, living area, and bedroom number 1, as well as the patio. So you'll see later a more clear drawing of the walls that are involved in my calculations. So here are some drawings that I will be using for this computation. First, move your eyes to this first square on top, which is labeled as the area to investigate. So this is the clear drawing I was talking about, involving dining area, living area, bedroom, as well as the patio. So we also need to consider the specifications. So for exterior walls, we must use 15 by 20 by 40 cm concrete hollow blocks. For interior walls, we use 10 by 20 by 40 concrete hollow blocks. On the upper left, here is a standard typical size of a CHB. Specifically, this reflects the 10 by 20 by 40 CHB. And here we also have other drawings of the left, right, and front elevations, as these will be showing the different walls that we will be considering, including the doors and windows that will be subtracted from our calculated number of CHB. So let us begin here with the calculations for solving the number of CHB. So let us direct our eyes to the left side of this image at the front elevations. Here you can see that there are two methods being used, the direct count method and the area method. You'll see that throughout the computation for the elevations, that the answers for both methods will be just the same. So in the end, we have one unanimous decision for both methods overall. So let's start. For front elevations, we have a direct count and area method. You can see that we do it twice for each method because for our computations for front elevations, it was divided into two parts. So for direct count, we get 89 CHB, and for area method, we get 86, which is close enough. And for direct count, for the second area and for the area method, we get the same value, which is 114 concrete hollow blocks. Moving on to the upper right, here we have the left elevation. Here we get 151 concrete hollow blocks. Next, for the right elevations, we get 179 concrete hollow blocks. And for the interior walls, we get around 127. So you may be wondering how we solve for each of these. So for the direct count, a quick summary of it is that we simply get the length, the dimensions, the length and the height of the walls, and then we divide that, each of them, by the length and the height of their respective CHB. For the area method, we instead take the area dimensions of each of the walls, and we divide it by the area dimensions of each of their respective CHB. And that's it. With this, we get a total of 533 concrete hollow blocks with a size of 15 by 20 by 40 cm, and 127 CHB for the interior walls, sized 10 by 20 by 40 centimeters. Next is relatively simple. We are solving for the mortar fill and for the mortar plaster. So for both of these, we simply get the area that is required for each of the walls. So it's just the area of the wall, minus the doors and the windows and the columns that are within it. And we multiply it by a coefficient depending on their class or depending on whether it is for cement or sand. Then we calculate for the number of bags required for the cement and for the cubic meters of volume for the sand. So let's start with solving for mortar fill. So for mortar fill, there is one method, which is the area method. Here we have the front elevation. We have an area of 15.908 square meters. For the left elevation, that's 12.06. These calculations were shown in the previous slides, as they are just the same. It's just the area of the wall. Right elevation is 14.275 square meters, and for the interior wall, it is 10.15 square meters. So if we refer to the interior and exterior wall sizes, which is for the CHB, I mean, which is 15 by 20 by 40 and 10 by 20 by 40, because these calculations will depend also on the size of the CHB, we get that for the exterior walls, we have cement. We need cement bags of around 65 bags, and for sand, we need 3.566 cubic meters. For the interior walls, which is the 10 by 20 by 40 CHBs, we need around 9 bags of cement and 0.442 cubic meters. So this totals to 75 bags of cement and 4.008 cubic meters of sand for the mortar fill. Next up is the solving for mortar plaster. So here we refer to it being class A and using 8 millimeters. So for cement, we calculate it by multiplying the area by a coefficient that is dependent on the class that was used. Then we multiply it by 2 to cover both the outside and the inside, or both sides of the wall. This leads to a cement of around 16 bags of cement, and the same calculation is done for sand with a different coefficient. It leads to 0.839 cubic meters. So this totals to 16 bags of cement and 0.89 cubic meters of sand for mortar plaster. So moving on to the final slide for our sample calculations, here is the solving for the reinforcing bars and tie wires for the masonry works. So for this, there are actually two methods. Once more, it's the area method and the direct count method. So let's first start with the area method, which is the simpler of the two. So here, what you need to do is to get the total area of the walls, and using 40 cm spacing, and that the horizontal bars are layered every 3 CHB. We have, for the vertical bars, we get the area of 52.393 and multiply it by 2.93 to get 153.52 meters total of vertical bar length. For the horizontal bars, we get the same area, multiplied it by 2.15 instead, and we get 112.65 meters. This totals to, let's skip the tie wires for a sec, the number of rebars. You get the total of those two lengths that we just computed and divided by 6, and we get around 45 bars required for the reinforcing for masonry works based on area method. And for the tie wire, this is based on standard computations. You multiply the area by 0.047 and you get 2.463 kilograms. That's it for area method. Next up is the direct counting method, which this method is actually very difficult. It was in fact so difficult for me that I decided that it would take too much time, and I opted to overestimate everything by ignoring all the columns, doors, and windows in the computations. So these will use just the areas of the walls themselves, similar to area method. But instead of using the area dimensions, we will be using again the base dimensions and the height dimensions for each of the CHB and for the walls themselves. So here, there's separate calculations for vertical bar and horizontal bars. Let's start with the vertical bar lengths. Here we divide 5.05 by 0.4, 0.4 being the spacing, and we get that we need 12.625 vertical bars, and we do that so on for all the walls, and we get 62.375 vertical bars. With that, we multiply that with the required length of each vertical bar, which is 2.9 plus 0.2 for the extra length at the ends, and we get 193.3625 meters. We do a similar thing for horizontal bar lengths, and we get 103.8 meters. Then we add those two totals together, divided by 6, and we get that we need around 50 bars of rebars of 10 millimeter diameter at 6 meter apiece. Then for tie wires that we are required, for direct counting, there's also standard procedure. There it is, and we get that the tie wires we need is on 1.42 kilograms. So that's it for the calculation of the reinforcing bars and tie wires, both area method and direct count. So to summarize yet again, using area method, we get 45 bars and around 2.460 kilograms of tie wire. But for direct count, we get 50 bars and 1.42 kilograms of tie wire. So both methods are different.
For our manpower requirements, on this slide we break down our manpower requirements into 5 key operational phases to ensure every stage of construction is appropriately staffed. For management and supervision, our personnel and rates, we have 4 key staff members, including a project engineer, site engineer, safety officer, and timekeeper with daily rates of 600 to 1,200. And for our site prep and structural works, our personnel will be doing the heavy lifting phase, requiring an equipment operator and a large crew of masons, carpenters, and laborers, totaling 18 personnel, with daily rates of 500 for laborers and 750 to 800 for skilled trades. For architectural works, including masonry, roofing, ceiling, and finishing, our personnel includes 21 personnel with roofers, painters, tile setters, and ceiling installers, with daily rates of 750 for skilled roles and steel fabricators at 800 pesos. For our MEP works, or mechanical, electrical, and plumbing, our personnel will consist of 7 people, including specialized electricians, plumbers, and AC technicians, with daily rates of 800 to 850. For the final cleaning and turnover, our personnel will consist of a final team of 3 laborers or helpers with daily rate of 500 pesos.
Hello, I am Nico Kamins, and I will be talking about the detailed estimate of our project. So first of all, we have the general requirements and earthworks. The detailed estimate begins with the general requirements, which cover project mobilization and demobilization, permits and clearances, temporary facilities, and health and system provisions. These items are essential for project startup and regulatory compliance. The estimate then begins to the earthworks, which include site clearing and grubbing, structural excavation for footings and tie beams, backfilling and compaction, gravel bedding, and termite treatment. These activities prepare the site and establish a stable foundation for the structure before construction of the major structural components begin. Next, we have the structural works. The largest portion of the estimate is allocated to the structural works, consisting of concrete and reinforcing steel. Concrete works cover the construction of wall and column footings, columns, suspended slabs and beams, slab on fill, and stairs. Among these, the suspended slabs and beams represent the highest concrete cost due to their volume and structural importance. Reinforcing steel requirements include 16 mm, 12 mm, and 10 mm deformed bars, along with the GI tire wire, and these materials provide the necessary strength and durability to resist structural loads and ensure the building's long-term stability and safety. Next, we have masonry and formworks. The estimate also includes masonry works such as exterior and interior concrete hollow block wall construction and cement plaster finishes, which account for a significant portion of the project cost because of the large wall areas involved. Formworks and scaffoldings include phenolic, plywood, coco lumber, nails, and steel scaffolding. These are used to shape and support concrete members during construction. The detailed estimate also includes thermal and moisture protection works which provide weather resistance and thermal comfort for the building. These consist of a 0.50 mm pre-painted rib-type roofing, double-sided P-foam, roof insulation, a pre-painted flashing and ridge rolls, box cutters, and waterproofing for balconies and toilet and bath areas. These components protect the structure from heat, rainwater intrusion, and moisture-related deterioration. The estimate also covers doors and windows, which includes the main solid panel door, interior flush door, PVC or aluminum, doors for toilets and baths, aluminum sliding glass windows, awning windows, and balcony sliding glass doors. These elements contribute to the building security, ventilation, natural lighting, and architectural appearance. The estimate further includes ceiling works consisting of fiber cement boards on metal furring systems for interior ceilings, moisture-resistant ceiling boards for exterior eaves, and cornice or shadow line details. These materials improve aesthetics while concealing structural and utility components. And tile works also include homogeneous floor tiles for the ground floor, wood plank, ceramic tiles for bedrooms, non-slip tiles for wet and outdoor areas, glazed wall tiles for toilets and baths, and tile adhesive and grout. These finishes enhance durability, cleanliness, and visual appeal. In addition, painting works cover exterior elastomeric paint, interior semi-gloss latex paint, ceiling paint, and wood and metal protective coatings. These finishes protect surfaces from weather and moisture and corrosion while improving the overall appearances of the residence. The estimate also covers the building's mechanical, electrical, plumbing, and fire protection systems. Electrical works include rough-ins, wirings and cables, lighting fixtures, switches, and convenience outlets, panel boards, and circuit breakers. Plumbing works consist of sanitary and waste lines, water line systems, plumbing fixtures, septic tanks, and drainage structures. Mechanical works include split-type air conditioning units, exhaust fans, and range hood provisions. And beyond the building itself, the estimate includes the fencing works, such as perimeter, concrete hollow block fences, and steel gates, as well as the site development works, including the landscaping, grading, driveway paving, and pathways. Together with the structural and architectural components, these items ensure that the residence is fully functional, safe, accessible, and ready for occupancy.
For the summary of bill of quantities, from an estimating perspective, this is where we see the total financial footprint of the project. And we're going to be discussing it into four key areas. First is the direct costs. Our total direct costs, which covers all the physical materials, labors, and equipment, comes out to 6.2 million pesos. If you look at items 3, 4, 5, concrete, steel, and masonry, you'll see that they are our biggest cost drivers. Together, they represent over 50% of the direct budget, which is typical for a structurally sound building. Second is the indirect costs. We have calculated 1.98 million pesos in indirect costs. This is based on a 32% markup applied across the board. In estimating, this is crucial because it covers our OCM, or our overhead contingencies and miscellaneous, plus the contractor's profit. Third is the grand total. When we combine our direct and indirect costs, our final bid price or contract value is 8,187,549 pesos and 22 centavos. This is the number we use to perform a sanity check against the floor area to ensure our cost per square meter is competitive in today's market. And finally, our strategy. This estimate isn't just a guess, it is directly linked to the manpower schedule we discussed. By aligning our labor count with these budget line items, we ensure that the project is both financially feasible and operationally realistic.
The prices used was based on cost, availability, and overall material quality. We selected the materials that were the most economical and readily available for the estimate. And for the method used, we prefer the fundamental method for structural and detailed computations. We use this method because it is highly accurate and computes the exact quantities of materials, labor, and equipment needed. We also utilize the area method for preliminary cost estimation because this approach is faster and simpler to apply, making it particularly useful for estimating larger building areas. When determining the OCM and CP, we relied on standard construction estimating practices. These standard costs account for supervision, administrative expenses, transportation, and contingencies. We consider our final estimate to be highly competitive in the current market because our prices are grounded in actual local quotations, we compared multiple suppliers, and we deliberately selected economical and available materials. During the preparation of this estimate, our group encountered several key challenges. We had to deal with the limited availability of some items, managing the time-consuming process of quantity take-off computations while maintaining a high level of accuracy in our detailed estimates proved to be quite demanding. And that is all for our final reporting. Thank you.